All right, this is our first example of doing one of these types of problems that I call a rice table problem. And we're going to write in the equation that we have up here, having carbon dioxide gas, hydrogen gas, and we have the back and forth arrows, carbon monoxide, and water vapor. Having all these guys together, we're trying to fill in this table. R stands for reaction. I stands for initial conditions or a value. C stands for change that it goes through, and E stands for equilibrium. All of these values we have up here are initial, so a mixture of these things are placed in a container, initial conditions. So I have all these initial pressures available. So carbon dioxide is 4.1, and everything in this table are ATMs. Hydrogen gas up here is 2.05. I don't have any carbon monoxide present, and water vapor is 3.28. And from here, I look for any additional information, and I find some. At equilibrium, looks like the water vapor has a pressure of 3.51. So it changed. And by how much? Well, it looks like it went up by about 0.23. And for the fact that this went up by that, and it came from the reactant side, this has to be the exact same value that it went up by. And then I continue that value, of course, at equilibrium. And if these went up by that amount, pay attention to the coefficients up here. So stoichiometry, they happen to be the same number. These all went down by that exact same amount. And I just do the math, and I'll end up with 3.87 and 1.82 over here. All right, fantastic. Calculate the equilibrium partial pressures of the three, and okay, I did them all, so there they are. Then it asks us to calculate Kp for this particular reaction. So all you got to do is take these values that are present. They all happen to be pressures. So it's the pressure of this over the pressure of those two guys. I am going to plug those into an equilibrium expression. And then just do the math. Ends up equaling 0.115 is the answer, which is equal to, again, Kp. If I wanted a Kc, I could go ahead and do the conversion process over to that. It didn't specifically ask for that, but it does do it here in this problem. So if I take a look and say, okay, the equation for that, Kp is equal to Kc RT to the delta N, and I can plug in all these numbers, but if I'm clever, if I take a look at this little factor up here, 1 and 1 minus 1 and 1 makes 0. Anything raised to the 0 power is 1. Therefore, these two values are equal to each other. I'm not going to do any other calculations. I'm simply going to say it is 0.115. And that is the last part of that problem. 47, let's see, do I want to do that one now? Sure, why not? My notes are a little wonky here. It actually continues over on the other side, but I'll at least mention it here. At 100 degrees Celsius, Kc is 0.078. So I go over to this one here. There it is. 0.078 is the value. I'll write that over here. Kc is equal to 0.078. So I have that value, and it says you have equilibrium mixture of these three gases. The concentration of these are boom, boom, respectively. What is the partial, sorry, pull it down. What is the partial pressure of the chlorine in this mixture? Okay, so the easiest way to take a look at this one is first just to set up a rice table. And then we'll start putting in the values that we can find for this. So looking at the kind of setup here, it's a little bit tricky because we just kind of want to start throwing numbers around. But we have to be careful about what and where we put these numbers. So in the equilibrium mixture of the three gases, at equilibrium, so we're already here, it says, the concentrations of this and this have these two values. Okay, it wants the value of the third one. So kind of interesting, clever, tricky problem as far as the things we have. So I'm just going to write in what the problem gave us. It did not give us the Cl2. That's a Cl2. So we have to figure it out. But it did give us the actual answer, if you will, for Kc. So I'm actually going to put this together. 0.078 is that answer. And I'm going to put in the products over the reactants for what I have and don't have. 0.052 for the SO2. I'll put an X for what I don't have. And then the reactants concentration, equilibrium concentration is right here. Also be aware that these are concentrations. And if I solve for the missing variable, the Cl2, I will find that that answer is 0.162. And again, that is a molarity of Cl2. So that's a point for celebration, kind of exciting. But we're not 100% done because it actually asks for a pressure of it. We have the concentration. And previously, it did tell us what some of the starting conditions were. It said it was 100 degrees Celsius. And here is my concentration for that. So let's go ahead and see what else we can kind of put together here. We're thinking Pivner. So I'm going to say P is equal to nRT over V. And I don't know if we had a pressure in here or not. I'm looking on my sheet here for that information. I'll figure that out in a minute. Yeah, it just kind of escaped me here. Molarity. Molarity is moles per liter. All right, so let's go ahead and put these values together here. I will break molarity down to moles per liter. So again, PV equals nRT, so I've got a couple taken care of here. I have my R value, 0.0821. We're dealing with ATMs. We want ATMs. And 373 Kelvin, it gave me 100 degrees. So make sure you change that over to Kelvins. And if I do all this little math here, you'll end up with an answer of 4.96 ATMs for the answer. Outstanding. All right, I think we got a little bit of notes left here. Well, let's go ahead and just march into 63. Why not? All right, consider the following equilibrium for which the delta H, remember chapter 5, delta H is less than 0. So that means it's negative, which means it is exothermic. So I'm going to actually write in the word energy here. So pretend it is a thing. Fantastic. All right, so if I take a look at this and say, all right, well, how will this go? How will each of the following changes affect the equilibrium mixture of the three gases here? Oxygen is added to the system. Oxygen is added. So here's oxygen. If I add some oxygen, it has to shift to the other side. It's going to respond. So we will say shift right. Let's slide over to B. The reaction mixture is heated. Here's energy. If I add some, it has to shift to the left. I'm just going to write an arrow left. C, the volume of the reaction mixture is doubled, so I make it larger. I have 3 on the left, 2 on the right. So it allows for more space, So I'm going to shift to the left because I have more stuff over there. A catalyst is added, tricky. The overall activation energy is lower, but in regards to a shift at all, it has no effect at all. E, the total pressure of the system is increased by adding a noble gas. The total pressure of the system will go up, but as far as a shift in either direction, also no effect. There are no shifts. SO3 is removed from the system, so I take some of this away. So in order to replace it, I have to shift to the right to replace that amount. And of course, the energy will go up as well. Temperature will increase. All right, fantastic. That is the end of the lecture.